Okay, so in the previous one, I suggested that you go to this trig tour and you play with it to see that it answers our problem. We have these two functions, cosine theta and sine theta. Theta is this angle right here, and cosine and sine theta create this circle. And if we take the angle theta, this is the angle theta is coming along here, and we just plot where we are in y, we plot where we are in sine theta or cosine theta, it's going to give us these wavy things that we can use. And you can see that sine and cosine are pretty similar. They're just offset from each other as far as what we're talking about today. So this answers our problem of knowing whether, let's see, so if we call this the, we'll go out here and we'll say that Nick is holding on to this bead, and we say this is the wave front. And if we want to know our phase, which is where we are in this wave, we can see that if this is the wave front, that is a theta of 631 degrees. And that if we go here, there's our peak, there's one point, and this tells us we're at different places. And so we can use this to tell us where we are in the wave. Okay, let's watch this. So it starts out at 0, goes to this point, which is 90 degrees. It goes here, it goes here, it goes here. This whole circle describes one wave. So that's how this wave angle, you can see this happening. Let's go back to 0, start here, go here, go here, go here, go here. One full circle is one full wave. So I can divide by 360, see what my remainder is, and that will tell me where's my up-downness, where am I headed next inside of an oscillating wave. So that's why we use the sine and cosine functions to talk about wave. And when we're talking about phase angle, remember phase, where am I in this wave? Angle means I'm using one of the trig functions so that I can tell where I am in that wobbliness. All right, so theta is the phase angle. Okay, and I say here, phase is about, oh, I'm going to catch all my errors in this. That'll be good. That would be good if I caught all my errors. I'm sure I didn't. Phase is about a place in space and time, okay? And yes, we're getting really, really close to space-time. All your work will be rewarded. There is also a when involved in phase, where I am in the angle. So if we have an oscillating wave, so now we're talking about Jason sending it to Glenn, and let's go back to our wave on a string. So we're done with the trig simulator, unless you're doing the math path. Okay, so Jason is oscillating. Plug my laptop in. Jason is oscillating, and he is sending it to Glenn, and Glenn is receiving the energy. Now, Ella is going to help. Ella has a second rope or piece of string, and she also is going to send energy to, oh, I have to turn my damping back down to none because it's getting too, that's why it's getting less. Ella is also, so there are going to be two strings, and Glenn is going to hold on to both of them in one hand. And what Jason and Ella want is for Glenn to receive twice the energy of the wave. So Ella is going to use exactly the same function, sine theta, that Jason is. And if Jason and Ella are using exactly the same sine theta, then they both are producing the same wave, and what Glenn will feel will be twice. It will be the addition of both the waves. What this is called, when it's perfectly aligned like this, is called in phase, and that is an important concept.
So I put like double. There's like orange next to green. Okay. This is also called constructive interference. You think of interference doesn't sound constructive. Sorry, interference doesn't sound like it's a constructive thing, but constructive interference means you're getting more. So Glenn's going to feel twice as much when he gets to the peak energy than he would if Jason or Ella were operating by themselves. Now, the second situation is, what if they're both going to use the same sine theta? Both going to use the same sine theta, but Ella is going to get started a little bit early. So if we start Ella a little bit early, then what Glenn will feel is he'll feel nothing until he first starts to feel Ella's wave. And then when Jason's wave gets to him, he will feel Ella's plus Jason's wave. Ella's plus Jason's wave. Now notice that this never quite gets back to 2 or -2 like we had before. That's because there's some of the up-downness of both waves is acting against each other, and we never get the perfect peak helping peak, which is what resonance will be really important about, peaks helping peak. So these are not in phase, but they're not quite yet 180 degrees out of phase. We can change this so that Ella's start is so far ahead that she is 180 degrees out of phase. And you can play with that on the trig simulator. What that will mean is when Ella is done with her first peak and she's starting her trough, Jason is starting his peak. Ella's still going to start ahead of Jason. What Glenn will feel is nothing until he first feels the first part of Ella, where it's just Ella, and he'll feel just Ella. Then, when Jason's wave hits, it's equal and opposite to Ella's. It's exactly equal and opposite to Ella's. They cancel each other out, and Glenn will feel nothing. If this is a light wave, what Glenn will see is light, light, light. I'm sorry, nothing, light, nothing. We're going to see this as dark bands when we see our interference from our double slit experiment, when we prove that light is both particle and wave. It's going to be bands, dark bands, and we're going to see dark bands when it destructively interferes, and we're going to see bright bands when it constructively interferes. Okay. Destructive interference is how works for all kinds of waves. It's how noise cancellation works, active noise cancellation. So some earbuds that say they're noise cancellation are really just cushions to prevent sound from getting to you, or some kind of blocking device. But active noise cancellation has a little listening device, a microphone, that picks up noise as it's coming in. It uses electricity, and it produces an equal and opposite wave to the waves that it's coming in to try and make those zero as they come into your ear. Now, it won't do it perfectly, but it will knock out a lot of the noise, and that's why these noise cancellation things work. So this works with all kinds of waves, with water waves, with light waves, with sound waves, constructive and destructive interference. And to have perfect noise canceling headphones, you want them 180 degrees out of phase. All right, we're going to take a little break there because my puppy was just let out, and this is a good breaking point. So I will end this section. I'll see you in the next section.